Last time we started section 2.2, which was describing sets. We had a lot of vocabulary, and I think we ended up ending right here. Does that look right? Okay. So we had talked over on this slide about complements and how complements are everything in the universal set, whatever that is, that are not in the set that's sort of smaller than that you're describing or isolating some sort of portion of. The example we had given was female students compared to all OBU students, where the complement would be the male students at OBU. So we're going to take a look at a different one, very similar, but different one. So U is the set of all students at OBU, and then A is the set of the students who are graduating. And this one simply asks us to describe what the complement would be. So notationally, of course, complement we did last time has this line on top of it like that. So what would this be describing, or how would we describe the complement of this particular set?
All the students not.
Yeah, these are our OBU students who are not graduating. In a very real sense, as faculty members, we get two lists towards the end of the year, graduation lists and recruit back lists, making sure that we've connected with all our advisees and everybody's got a schedule and they're all logged in and all that good stuff. So this is a very real sort of description that we get as faculty members at the end of our semesters. Venn diagrams, talked about again before, but we're going to keep sort of developing this idea. A subset. So if we have two sets A and B, and all of the items in A are also in B, then we would say that A is a subset of B. And it's written like this. I wrote it backwards according to how my description was. Sorry. B is a subset of A is the way I've got my description. So B is a subset of A. There we go. It's curly. It's kind of like a less than or equal to symbol, but it's got a curve to it instead. So sometimes I have people who write it, and I think it looks more like a sideways U, but they'll think it looks like a C. C's to me are fatter than U's, but whatever. But it's like a C with a line underneath it. So one of the ways that I tend to describe it is more like a less than or equal to kind of a symbol. When we think about, I'll use numbers actually, 3 being less than or equal to 4, we mean that it's smaller, right? That's one possibility. Or while it feels weird, I could actually write this, and it would also be true, or equal to. Okay? So it's kind of that same idea. B is smaller than or equal to A, so they could actually be the same thing, but it also has this extra feeling of being contained inside of. So in terms of a picture, it looks like this. You've got the circle B and the circle A. Whoops. That was supposed to be another circle. And one of them is contained inside of the other one. So since my B is my subset, we're saying that B is contained inside of set A. So B is smaller than, it's inside of set A. But the reality is they could actually be exactly the same set, so that this picture is sort of misleading. Everything's really inside the little circle, and there's nothing in this outer region, sort of like a reverse donut or something like that, okay? So this is the idea of a subset. It's something that's inside of something else. Now, if it's really smaller than it, like it really, really is inside, not just sort of this less than or equal to weirdness where I can say 4 is less than or equal to 4, and we're like, well, I mean, okay, but why? Why would I describe it that way, right? So if it's really inside it, but it's really smaller, then it's called a proper subset. So if we have sets A and B is a proper subset of A, it has to be a subset, and it has to have at least one more element in set A than we had in set B. It has to really be smaller. And the notation for it is quite similar. We simply lose the line underneath. It can't be equal. It really has to be contained inside and smaller. Okay, again, back to my less than or equal to kind of symbols. I can also write this one and it's true, right? But if I try to tell you this one, you should say, now wait a minute. Right? This isn't true. I lose some flexibility. I lose the ability to equal the set when I'm talking about a proper subset. So one of the questions that you'll be asked will be to find numbers of subsets. How many different, smaller things could you create? If you have n elements in a group, then there are 2 to the n subsets and 2 to the n minus 1 proper subsets. And if you would like, I can show you how that would work for something small so that you can see why it's working that way. We did this description once before. It was with a different context, but I talked about things having 3 items in it. So I will use a set with A, B, C in it. So it's 3 elements, right? So I should have 2 to the 3rd, which would be 8 subsets. And then 1 less than that, 7 proper subsets. That's what it should be. So you might think, well, what does that mean? Well, anything that's a subset means that it's smaller or equal to what I already have. So I could have a subset. The first one seems sort of silly, but we're going to write it down, and it is one. I could have the empty subset, the null set. Okay, that's one of them. Sort of by default, it's a subset of the other one because everything in the null set, which has nothing in it, is inside of the other set. Okay, so like that's one possibility. We could have all the sets that have the single letters themselves in it, A, B, or C. Right? Everything in each of those sets individually is inside of the large set I started with. We could have the set with 2 items in it, so that would be AB or BC or AC. Right? And then the last subset, which is the non-proper subset, is the set itself. Technically, everything in that set is in the other set, so it is a subset, but it's not smaller, so it's not a proper subset. So you can see that there are 7 proper subsets, right? And if we tack on the full set itself, we get 8 subsets. And of course, it works for bigger. I mean, if I had 4 elements, I'd have to do combinations of all things 3 at a time, and then the 4th one. Right? If I had 5 subsets, I'd have to do combinations of 4 things, and the 5th one that contains all of them, and we would continue the process. More elements, more subsets. It gets kind of big pretty quick, actually. So what if we had 5 subsets, or 5 elements? So consider the set of all mathematics faculty members at OBU. There are 5 of us. How many different subsets are there? So what would I do to find that? The answer will not be write them all out. So did you have an idea, Michaela? 2 to the 5th, right. So I'm just asked how many, not what they are. So this notation at the very bottom of the screen told me how I find that. It's 2 raised to the power 5. So 2 to the 5th. And if you're not sure what that number is, you haven't dealt with it recently, grab a calculator. What is 2 to the 5th? It's 32. So there are 32 subsets. And whether you get that right or wrong, you should still be able to answer the proper subsets question because it's always 1 less. So if there's 32 subsets, there would be 31 proper subsets. So like when I teach this course online, I always look at this one as a question. If they get wrong, they might get partial credit because even if they screwed up part A, as long as their part B goes with their part A, they're going to get partial credit. This is one of those places that is commonly partial credited on an online version. You bet.
So on there's 8 subsets.
Yes.
But there's 7 proper subsets.
Yes.
So
the first 7 are the 7 proper ones.
Mm-hmm.
Proper means they're already a subset. They're just smaller. And then the last one is also a subset, so there are 8 subsets total. Everything that I wrote down is a subset by definition. But the last one does not follow the proper subset description. It follows the subset description just like all the rest of them do, but it fails to be a proper subset.
Okay, sorry, I read the question wrong on number 8.
Okay.
Next one.
No worries. Any other questions? Okay. So this next question, number 6, kind of asks the question backwards. It actually tells you how many proper subsets you have and is asking you to go backwards to find how many elements you have or how many individual objects you would have in your set. Okay? So it says there are 63 proper subsets. So how many subsets total are there? Yeah, 64 total subsets. That's actually a relationship that exists, right? There's one more and one less of those. So if I have 64 subsets, how many elements would I have? Or how could I find it? 2 to the n would have to equal 64. That's exactly right. So what would n have to be to make that work? And you can do it by trial and error pretty quickly. It's 6. N would need to be 6 to make that work. So we have 6 elements. Does that make sense? Okay. I tend to confuse people with this question sometimes, so I want to be sure that you see that question 7 and question 8 are very similar. The directions are different, but the statements themselves are the same. So look at your question 7 and your question 8, and notice A, B, C, D is like a copy-paste argument from my slides. Do you guys see that? Okay. The questions are very different, though. So let's see. On question 7, it asks us to identify which symbol, and the symbols refer to element or not an element. And question 8 refers to a subset or not a subset. So there's nothing special about the fact that I'm using different directions with the same solutions or the same questions. It just works really nicely to talk about both of them because we've already familiarized ourselves with them once, so I don't have to go through that again for another set of questions. Does that make sense? Okay, so please don't confuse yourself and think that you're going to be asked to figure out which of these 4 items goes in the blank. That's not the deal. You're going to be asked questions very much like this, and they'll just have different parts to them. Okay, so this one right here, question 7, asks us about element or not an element. Okay, so the elements are the individual objects inside. So this question is asking if the thing, there's 2 questions, number 1. The number 1 question it asks you is the thing on the left even an element at all? And if it is, then you can ask yourself question number 2. Question number 2 is it contained in the set that's described on the right? So looking at what we have here, what is this thing representing on the left? It's the null set. In fact, you used the word set, right? What is on the left here is not an element at all. It's a set. Are you with me? So this one is not an element, and I don't even care what's on the right-hand side because this is a set. It's not an element at all. So I'm going to try to write down the whys for this. That way when you go back and either listen to this or check your notes, you'll remember why we said it. Why did we say it was this versus that, okay? So let's go to the next one. Is this a set or is it an element? It's an element. What would it look like if it were a set? It'd have curly braces, okay? So that's good. Empty set's a little different. You know, it's got its own notation. But most of the time when we're dealing with sets, we've got curly braces. So this is an element. So I continue asking myself the question, is it an element of what comes next? It is an element, but is it an element of what comes next? So is it an element of the things that are over here? So now we got to figure out what's over here. So Brianna, you're shaking your head, I thought. Does anybody, maybe not, maybe I just assumed. Does anybody know what's over on that side? What is that describing? It's set notation. We haven't done a lot with it, but we have seen it. Say again. Okay, so we see natural numbers. That's part of it. These are going to be natural numbers. Okay, so we're not talking about decimals and fractions. We're talking about natural numbers. But they're also natural numbers that follow this pattern. So if I use a natural number, what's the smallest natural number? 1. And I would plug it into this equation. What's 2 times 1? 2. And if I use the next natural number, 2, and I plug it into that equation, what is it? 4. And if I use the next natural number, I get, what numbers is this describing on the right-hand side? Evens. These are even numbers. Does everybody see how we got to that point? That they're even numbers. So, is 15 an element of the even numbers? No. So again, this one fails to be an element, but for a completely different reason, right? It's an element, but it's not even. So that's why it's failing. How about C? What's wrong with C? I'm getting nods that are saying no, that it's not working. It's a set. This is a set. So that's going to, it's kibosh right there. Can't do anything else. It's a set. I don't care what's on the right-hand side. We'll talk about it on the next slide, actually. But it doesn't matter. It's a set, so it's completely irrelevant what comes next. How about this next one, 16? Set or element? Element, cool. So it stands a chance, right? It's an element. Is it an element of what's on the right-hand side? Yeah, that one's easier to see, but it's actually the same set that number 2 was, right? It's the same even numbers we had before. It's just written in a listing method or the roster method instead of in set builder method. So this one actually worked. Yay, we got one that worked. We did, that was good. All right, so this one is an element. Okay, yes, Colton.
When we're doing our homework and we have some of these come up, are you going to want us to explain why we have the answer?
Only if it says that you have to. So if it doesn't have you explain, I'm not going to assume that you would know necessarily that I want you to. Like, it's okay that you don't. You can follow whatever directions it gives. Okay. However, I guarantee you on the test I'll ask you to explain. So it's your fault. I mean, it's your choice whether you would like to practice that now or not, but I'll ask you later if I give this question on the test. Okay? All right. So shift gears. The question is different. My sets and my stuffs are still the same, but the question is different. This question now says that I want to know if it is a subset or not. So again, subset means everything in a set on the left is contained in the set on the right. Inherent in that description is you have to have a set, right? So if you take a look at number 1, you have a set. So I stand a chance, right? So kind of like on the last one, I had to decide first, is it an element or is it not an element? Same thing here. I have to decide, is it a set or is it not a set? This one's a set. What about this one? It's a what? It's an element. In fact, I think I'll just go ahead and write that down now. This one's an element. I'll write it that way. How about on C? It's a set. And on D, it's an element. So the ones where I wrote element are automatically not subsets because they're not sets to begin with. Are you with me? Okay, so I got to make sure I'm talking about a set before I can even pretend that it might be a subset. Right? It's like I got to make sure that I'm talking to a woman before I even pretend to ask if she's a mom. Right? I mean, it doesn't make any sense. Okay? So let's talk about what's coming on the other side then for the ones that are sets. So the question now becomes, is everything in the set that's on the left inside of the set that's on the right? Now, I already did A before. I did it over here when I created all my subsets. Do you remember that? I told you the empty set kind of by default, the way the description and the definition always works. The empty set is always a subset because everything in the empty set, of which there's nothing, is contained inside of the other set. It's definitionally going to work, even if it feels kind of funny. So this one is a subset. Works. Okay, so number 4 is our last one. It asks if everything in the set on the left, the number 4, is contained in the set on the right. We haven't talked about the set on the right because we didn't have to on the previous slide. It's a funny way to write it, but what is really in the set that's on the right? Yeah, again, weird way to write it, but it's just the numbers 3, 4, 5, 6. So, is everything in the set 4 contained in the set 3, 4, 5, 6? Yes, it is. So this one is also a subset. And again, it's because there's only one thing over here, and it's also over here. Okay? Fundamental principle of counting is next. We used this once before. I didn't identify it at the time, so maybe you'll be able to tell me afterwards where we used it. The fundamental principle of counting says the following. If an event M can occur in little m ways, and an event N can occur in little n ways, then event M followed by event N can occur in mn ways. It's a really complicated way of doing something very simple. We're going to do the next example, and you'll see it used, and then I'll show you where I used it before. How many different outfits could be created from 3 shirts, 4 skirts, and 5 pairs of shoes? There are 3 events here. My events are, the shirt that I'm wearing, the skirt that I'm wearing, the shoes that I'm wearing. 3 events. There are 3 different choices for my shirts, 4 different choices for the skirts, 5 different choices for the shoes, and the fundamental principle of counting says that if I multiply these together, this is the number of different outfits that I can have. Nobody said they match. I have a daughter that likes to wear unmatching things all the time. It's kind of funny. Nobody said they match. What is 3 times 4 times 5? It's 60. There are 60 different outfits. Does anybody remember when I drew lines and I wrote numbers in and what they were for?
Factorial.
It was when we did the factorials. The example that I verbalized at the time was, I think it was ladies and gentlemen choosing for a date or something like that. Is that what it was? Yeah. So it was it was still a number of ways that something could occur, and that one turned into a factorial, like Hannah said, and she's right. So we actually see these happen quite frequently in descriptive problems, like in word problems. So I'm going to give you another example of that. So we're going to the mall. You have 6 favorite stores in the mall. And how many ways can the following happen? The first one says you have time to go to only 3 of them. Well, if you can only go to 3 of them, you only get to draw 3 lines. How many different choices do you have to go to the first place? 6. And we're not leaving and coming right back in. That doesn't make sense in context, right? I can't reuse the store. So when I go to my second store, how many choices do I have? 5. And the third store? 4. Fundamental principle of counting, I multiply. What is 6 times 5 times 4? 120 ways. There we go. What if you have time to go to all 6 of them? What will change? Yeah, there's 6 different lines, right? And I would end up with what happening? That same factorial that I got from the previous lesson, right? What is 6 times 5 all the way down to times 1? 720 ways. Now, the reality is that when we are going about solving a problem like this in real life, there's other factors we consider, like I'm not going to go from this store in the mall to the clear other side of the mall, right? Or maybe I found what I needed, so I don't even need to go to the other store that I thought I was going to. There's other things to consider, but there's actually 720 different orderings that I could use to go to these stores in the mall. Last example for today. I would like you to create a real life example of a null set in your life. And I'm going to write in the one that I talked about last time. The null set in my life would be the babies living in my home. That's a null set in my life. Notice I didn't say number of babies, right? The object, the elements, the things are the babies, right? The null set means that there's 0 of them. So the babies living in my home. So write something down for yourself. My notes say the monkeys living in my home, just so you know. Apparently monkeys was on my mind when I did it once before. Okay, who wants to volunteer what they have, just for fun? What do you have?
I did women in my immediate family.
Women in your immediate family. Be careful, because you're in your immediate family, so it wouldn't work.
Oh, so I count?
Yeah, you count. You would be an element of the set. Good try, though. I'm glad we asked. What do you have, Colton?
Null set of pancakes.
Pancakes what? Pancakes in your apartment? Pancakes in your dorm room?
Well, in my belly.
Pancakes in your belly. Okay, we can go with that one. What do you have, Aspen?
Cows on my farm.
Cows on your farm. Fantastic. What else? What else do we have? Any others? This is probably the first semester that nobody has volunteered the number of boyfriends in my life. Almost always have somebody who tells me boyfriends in my life. All right, very good.